Hi, this is homework 18 for ENGI 460. My name is Selassie Dumenu and my partner is Andres Cordova. Okay, so our problem statement basically wants us to sample from a density fx with the exponent of negative x squared over 2 with the proposal density q of y bar x, and that is equal to 1 over 2a on support x minus a, comma, x plus a. And we have our acceptance probability down there, which is the min of 1 comma the exponent open parentheses x squared minus y squared over 2. So like I said initially, we're going to be sampling from n 0 to 1 using the random walk algorithm, and basically the Markov chain Monte Carlo is what we are trying to procedure is what we're trying to implement here, and that will be represented by MCFC, and then we'll be coding this in MATLAB. So we're going to go over to MATLAB and then see how this is done. Alright, yeah, so for MATLAB we have our MCFC script already written, so I'm going to go through this briefly and try to explain what is happening in the code. So we have our function here. Our function z is our MCFC. Then we have our three inputs, which are our XO, our A, and then N, and our N is our number of iterations. And here we're saying XO is equal to XO, our Z1 should be equal to 0, and then our Z12 will be equal to XO. So that is going to create a matrix, a 2-column matrix basically when generating our z's, and then our for loop, which is for t equal to 2 to the number of iterations, and then our alpha here, which was in the PowerPoint, is our min of 1 comma the exponent negative 0.5 times whatever what was in the bracket, which is our y squared minus our z into bracket, z parentheses t minus 1 comma 2 squared, and then our r is rand, and then our if statement here is that if r is less than or equal to alpha, x new becomes our y, else our x new just remains at our z t1 t minus 1 comma 2. Then after that, after it runs through all of that, we have our t and then our x new, and then we want to see our z functions as well, but that is suppressed. And then for each one that we run, we want to see what the plot looks like. So I'm going to go ahead and then run this, and then when I run it, see, it wants me to input my arguments. So the first one I'm going to do is input this argument right here. I'm going to be using the RNG function. So my RNG is going to give me 59274. Now I put in my MCMC. Then we have our negative 4 as our XO. Then our A in this case is 0.5, comma 500 will be our N, which is our number of iterations. So when I click enter, gives our values, and this is what our graph looks like for the first one. So I'm going to go ahead and then close this, and then we'll see what happens when I run the RNG for the second one. Basically, I can just go up, actually get my RNG right here, enter that, MCMC, and then this time what we're doing is we're changing our A from 0.5 to negative 8 to 3. So our XO is going to be negative 4, then we have our 3, and then R stays the same at 500. Close that. When I run that, see that we have a slightly better looking graph with, as compared to the one that we had before. So a good thing to know was that because perspective variates are rejected, and because of that there is no change invariance from one iteration to the other. So now we're going to go ahead and close this and go ahead and try and generate the third scenario, which will be the same seed, but this time the iterations is going to run for 100,000. And seeing that we're going to get 100,000 points, our plot might look quite clustered, so we're going to go ahead and take our plot out, and then what we're going to do is we're going to try and generate a histogram of just the second column, which is the area that we are trying to analyze. Go to close that. And then, so if I go ahead, change that, I go ahead and run this, should clear, and then ask me again. So I go in here, put in my RNG, which is the same thing, and then for here, my MCMC is going to be -4, comma 3, comma 100,000, 1, 2, 3. Alright. Then when I run this, it should give us a histogram showing the distribution. Give some time to load or to run. There we go. And there it shows us what the distribution at 100,000 iterations will look like for this MCMC algorithm.